So let's introduce the concept of linear transformations. Transformations in general are just maps from one space to another space. We've seen examples of transformations whenever we're studying functions. We start off by studying functions which take one real number and map it to some other real number. So functions are just transformations from the real numbers to the real numbers. Transformations just go from one space to another space. So we think of transformations is a transformation is a map from one space called the domain to another space, which we'll call the codomain. I know some of you are expecting me to say range, but that's a subspace of the domain. A transformation is just a map from one space called the domain to another space called the codomain. So the notation that we'll use, because we've got to have notation because this is math, we'll say T is the name of the transformation, and we'll list the domain first. Let's say it goes from Rn to Rm. So T is a map that goes from Rn, which would be the domain, to Rm, the codomain. That's a transformation from one space to another space. What we do is to each element in Rn, we assign an element from Rm. To each x in Rn, that is, to each element of the domain, the transformation assigns an image T of x in Rm. To each element of the domain, the transformation assigns an image in the codomain. To each element of the domain, x in Rn is element of the domain. To each element of the domain, the transformation assigns an image in the codomain. And is called T of x. The way we visualize this, since we start off looking at transformations as transformations on Rn and Rm, real spaces, we usually just describe, say, the domain is a big rectangle. Here's our domain, which is Rn, and here's an element x in Rn. And over here, we'll draw another box for the codomain, Rm. And there'll be an image of x over here called T of x. X is a vector. So here, Rn is the domain, and Rn is the domain, and Rm is the codomain. X is the vector in the domain, and T of x is the image of x. And we say under T. And T is the map. We put an arrow here and say T, x on Rn, and produces vectors in Rm. Oops, scroll up. So x is from the domain. We apply T to x, and we get a vector in the codomain. That'll be the image of x under T. If you're wondering where range comes into it, the images, the set of all the images is the range, and it's a subspace of the codomain. The range of T is the set of all the images. The range of T is the set of images, and so that's going to be sitting in Rm. So there'll be some subspace of Rm, and that could be the range of T. It could be that the range of T is all of Rm. It could be that it's some smaller part of Rm. How's everybody okay? It only seems like we're going through this really fast because we're going through this really fast. Because the most important thing that you do is look at problems and try to think about what the problems are telling you to do. Get out there and do problems. That's the most important thing. So we're just doing some quick vocabulary. A linear transformation has some specific rules to it. A transformation T going from Rn to Rm is a linear transformation if then some certain rules have to apply. A transformation T from Rn to Rm is called a linear transformation if some certain rules apply. Its transformation is a linear transformation if it respects vector addition and scalar multiplications. Scalar multiplication. So we say it's a linear transformation if T respects vector addition and scalar multiplication. I got to clarify what I mean by this. What that means for all x and y in the domain and all scalars C, let's say in R, the image of a linear combination is just the linear combination of the images. The image of a linear combination is that same linear combination of the images. The image of a linear combination is the same linear combination of the images. That's the extra requirement for a transformation to be a linear transformation. The image of a linear combination is the linear combination of the images. That's what makes a transformation a linear transformation. Now the big thing about 1.8 and 1.9. What makes linear transformations, what relates that to stuff that we've done already? If a transformation is a linear transformation, then we can represent it with matrix multiplication. If T mapping Rn to Rm is a linear transformation, then there is an M by N matrix A such that T of x is just A times x for all x in Rn. That is, if a transformation is linear, then there is a matrix that implements the map. If T is linear, then there is a matrix that implements the map. A matrix transformation is a linear transformation. A linear transformation definitely has a matrix that implements the map. Any questions? Let's do some examples that will make everything trivial and easy. Oh, dang, we're out of time. So we are going to go over more about linear transformations on Wednesday. We'll also go over 1.5 and 1.7. We would not say matrix multiplication is a linear transformation. Matrix multiplication is just a matrix multiplication. A linear transformation is a different thing. We don't want to interchange things. We also don't want to say something like the transformation is consistent. That doesn't make any sense. Consistent is a word that we apply to equations. So matrix multiplication is similar to, will be a linear transformation, but we got to be very careful about how we say things. So I don't want to blanket say, yeah, what you said is correct. Does that make sense? So yeah, but let's be careful. A matrix multiplication is a I guess you could say a matrix multiplication is a transformation, but we really want to be careful about how we phrase things at this point. Because right now we're still saying things like the matrix is consistent, and we can't say things like that. So we got to be very careful about how we say things. All right, so let's pause the recording here, and we'll talk about what next steps are.